And then for people who would find it useful, the closed captioning is also.
Just quickly click on the got it part so that I can see my slides, and I'll restart again. There you go.
Thank you so much.
Well, thank you very much for a very nice introduction. Thank you for inviting me to present this colloquium. I will discuss today the results of our relatively recent study, and I will talk about the properties of dual active galactic nuclei that become eventually gravitational wave sources and host mergers of binary supermassive black holes. So I will first introduce my collaborators. The work that I will discuss today was mostly done by Kanya Lee, a graduate student at Georgia Tech for her PhD thesis, and in collaboration with David Ballantyne and Matteo Bonetti. Please interrupt me if you cannot hear well, and feel free to ask any questions during the presentation. That's totally okay, or save them for later. That's also good too. So dual AGNs, those at kiloparsec and larger separations, are actually our most definitive observational evidence that massive black hole pairs exist. And even more interestingly, these are the progenitors of massive black hole mergers and gravitational wave sources associated with them. You can see some number of examples here in this gallery from Mescu et al. And I will say that moving towards detection of massive black hole pairs at smaller scales, smaller than kiloparsec, and certainly smaller than a parsec, has been very challenging, largely because of a small angular separation of these pairs in the sky, which makes it difficult to distinguish two massive black holes, even if they are accreting, from a single massive black hole and a single AGN. So this is our best evidence that massive black hole pairs form in the universe. And the work that I'm going to discuss is actually motivated by some of these questions. So some of these massive black hole pairs will eventually end in mergers, but can we tell which ones are more likely to merge than others? How long does it take for them to merge? And which dynamical processes drive orbital evolution, and which are the most important for massive black hole pairs as a population, not necessarily on individual case-by-case basis? Also, can the incidence of dual AGNs on the sky can be used to predict the coalescence rate of massive black holes? And inverting that question, if eventually we measure the cosmological coalescence rates of massive black holes from, say, gravitational wave observations, are we going to be able to learn something important about dual AGNs on the sky?
And we have one question online.
Go ahead.
Before you go ahead.
Hi, Tamara. Quick question.
Yes.
So when you talk about massive black holes, this is just a terminology that I think people use differently. So can you please define, like, are you talking about supermassive black holes, or are you talking about sort of like an intermediate mass regime, like things that maybe live in dwarf galaxies, or like what is massive?
Excellent question. Okay, so let me just fast forward to the next slide. So when I say massive black holes, I generally mean 10 to the 5 to 10 to the 10. But for the purposes of this talk, I will be focusing on massive black holes with mass larger than 1 million solar masses. Let me explain why. So I will just introduce some most important aspects of our calculation so that you understand what's behind it. Basically, we start by drawing massive black hole pairs from the TNG 50 simulation. And TNG 50 is a part of a larger illustrious TNG suite of cosmological simulations. It has physical volume of approximately 50 co-moving megaparsecs cubed. So the important aspect that you just asked about is that in these simulations, black holes, when they're massive black holes, when they're born with a minimum mass of about 10 to the 6 solar masses. So in other words, basically the model assumes heavy black hole seed formation. And this will be important later on when we basically make predictions for coalescence rates and so on. There are about 2,200 MBH pairs within this simulation volume, and they reach minimum separation of about 1 or 2 kiloparsecs, which is set by the gravitational softening of the collisionless component, collisionless particles in the simulation, like dark matter and stars. And those black hole pairs, massive black hole pairs, are drawn from the simulation in a similar way that they've been drawn for some earlier works that basically focused on the illustrious sister simulation from this suite, as was done by Laura Black and Luke Kelly. We created a semi-analytic model to evolve massive black hole pairs to smaller separations due to the effects of stellar and gaseous dynamical friction in the merger remnant galaxy, due to the stellar loss cone scattering, due to the interactions with a circumbinary disk, and due to the emission of gravitational waves. But we do not take into account interactions with triple or higher order interactions with other massive black holes that may happen when the evolution of the pair is very long and there is another merger that brings yet another massive black hole on board. So those are neglected. Okay, this inset is basically showing the redshift distribution of massive black hole pairs when they're drawn from the TNG50 simulation. And you can see that it's a relatively broad distribution that extends to the redshift of about 5. And we'll come back to this distribution later. So our semi-analytic model evolves the pair in a merger remnant galaxy. We assume that there is a single galaxy at that point when they're at separation of about 1 parsec with a single stellar bulge and a single gas disk. We do not model the effect of the stellar galactic disk, because we find that it doesn't make a huge difference for the evolution of massive black hole pairs as a population. And consider 2 black holes non-spinning with the more massive one placed at the center of the remnant galaxy and the lower mass black hole placed somewhere in the disk of the remnant galaxy. So all our merger remnant galaxies are described by 7 parameters by the black hole pair mass and their mass ratio, by the mass and size of the stellar bulge and mass and size of the gas disk, as well as the rotational velocity of the gas disk. All of these parameters are informed, but all but the last one are informed by the values from the TNG50 cosmological simulation. And for the last one, we just make an assumption that rotational velocity of the gas disk is somewhere between 70 and 90% of the circular velocity of the galaxy at that given radius. So these are just the most important ingredients. There is more detail in this group of publications that I'm showing here in the case that you're interested in. And of course, you can always ask me if you have any questions. So let's first start with the timescales for evolution of massive black hole pairs as we calculate them from this model. So basically from kiloparsec, 1 or 2 kiloparsec separations down to merger. So on the left-hand side, let's just first focus on that histogram. This is a histogram of times that black hole pairs spend in the phase that is dominated by dynamical friction, generally from 1 kiloparsec down to about 1 or 10 parsec separations. And there are about 8,700 pairs in this histogram, which corresponds to the original number of pairs, 2165, drawn from the TNG50, times 4 different types of orbits that we consider in our model that include prograde and retrograde orbits and consider low or high eccentricity orbits. And in this histogram, you can see
Go ahead.
that, yes?
Does the prograde and retrograde here refer to prograde with the rotation of the disk and the orbit of the black hole, or what's the
Yes, good question. So the prograde means relative to the disk, or in the rotating in the same sense as the galactic disk, gas disk, or retrograde in the opposite sense from the gas
and
disk.
are they
Thank you.
all in one plane, or is it more of a statistical distribution?
The secondary lower mass black hole is in our model always placed in the plane, always placed in the plane of the galaxy.
I have another question. When you were describing how you set up your model in the previous slide, do you just use a snapshot of these properties when the pair forms, or do you allow these to evolve with time?
We just use a snapshot, basically, that is defined by the last snapshot in which the pair of massive black holes in the TNG50 simulation reaches the minimum separation. So from that snapshot, we draw information about the galaxy around the more massive black hole, about the stellar content and gas content, and that's what we use to describe the remnant galaxy. We don't evolve these properties with time.
Okay.
And what does it mean to be stalled, but add a dynamical friction time scale of 10 to the 8 years?
Okay, so that's a good question. You can see in this panel that basically timescales for evolution are long, but for some, there are two groups here that are marked with hatched bars that don't coalesce within a Hubble time, or by redshift of 0, actually. And for those that stall, that group around the time of 10 to the 8, 10 to the 9 years, they actually stall at smaller separations. So they don't stall necessarily while they're in the dynamical friction stage, but they stall when they move to separations where stellar loss cone scattering dominates. So their dynamical friction time is kind of reasonable. It's on the order of 10 to the 8, 10 to the 9 years. But later on, basically, they stall.
Well, that's super interesting. Okay.
Right. Yeah, there are some very diffuse extended galaxies that would basically lead to that kind of evolution. For the others, they basically exceed a Hubble time already in the dynamical friction stage, and that's the last group of bars that falls around 10 to the 10 years.
Amazing.
Okay. Any other questions? If not, let's move to the next panel. So for those black hole pairs that basically evolve successfully through the dynamical friction stage, they become gravitationally bound, and they become subject to other dynamical effects that lead to the orbital evolution. At those stages for gravitationally bound black hole pairs, stellar loss cone scattering tends to dominate, or interactions with the circumbinary disks, and eventually emission of gravitational waves at the smallest separation. So this middle panel is showing the timescale for those three mechanisms. And you can see that, okay, the timescales are a bit shorter, a good bit shorter than for the dynamical friction stage. They're about 10 to the 7, 10 to the 8, and there is actually a broad range. So adding all these up together gives us the total time to merger from 1 or 2 kiloparsec separation down to coalescence. And what I wanted to basically highlight here is that this last histogram looks very similar to the first one, minus the bars for the stalled pairs, you can see the dynamical friction is the dynamical friction stage is the defining one, effectively, that determines whether a majority of the sample will coalesce or not. And that's interesting because from theoretical point of view, A, you know that this is the bottleneck, but B, if you take a set of dual AGNs that you know are likely to merge, you only need to model them through the dynamical friction phase, and you can obtain a reasonable estimate for the coalescence rate of massive black holes. You can neglect evolution at smaller scales. Although individually, you don't know which pair exactly will merge and which one will not. But you will get a good estimate. Yes.
What is the denominator here? This looks like the total number of the 8,860 pairs. So what was the volume of the simulation?
The volume of the simulation is that of the TNG 50, which is about 50 kiloparsecs, moving kiloparsecs cubed.
So what does that turn into in terms of a rate per cubic picoparsec, let's say?
I don't know. Let me divide at the end, divide by the volume at the end of the presentation. But presumably it's basically the density. You're probably asking about the density, cosmological density of massive black holes per unit megaparsec cubed or something like that. We can calculate it, but it's basically whatever is given by the TNG 50 simulation. Plus we model this 4 different configurations here. So for us, it's just a sample. The number is not important just yet.
Thanks.
Yes. I see that there is there a hand up?
I think that's
no,
left
that
earlier.
Okay. So I will move on, unless there are any other questions at this point. So there is also a second interesting implication of the fact that the total time is determined by the dynamical friction stage. And that is that if you measure a coalescence rate of massive black holes from gravitational waves, you will be directly constraining the efficiency of dynamical friction, effectively. So we'll keep that in mind, and we'll move on to basically look at the redshift distribution of massive black hole pairs that merge from this sample. So I showed you already the panel on the left. This is the initial distribution of massive black hole pairs as they're drawn from the TNG 50 simulation. So it's a relatively broad distribution. When we evolve them through all the dynamical processes that I mentioned, and when we plot only the coalescing, the group that coalesces, the distribution at merger is shown on the right. And you can see that at the time when they merge, most mergers occur at relatively low redshift, mostly below the redshift of 2, which is good news for the electromagnetic follow-up, potential electromagnetic follow-up of these sources. You can see that because we distinguish between the prograde and retrograde orbits, prograde orbits are a bit more favored in the sense that they will lead to a higher fraction of coalescences than retrograde orbits. And this has mostly to do with basically dynamical friction, which depends on the Mach number and relative motion of perturber through the gas. So it matters whether it orbits in prograde or retrograde direction relative to the galactic gas disk. So we get that 71% of prograde pairs merge as opposed to 39% of retrograde pairs. Okay, so that's that distribution. Let's look at the properties of those systems that actually lead to massive black hole mergers, because this is what we're hoping to understand. The first panel on the left shows the coalescence fraction as a function of the gas fraction of the merger remnant galaxy. And the gas fraction is defined just as the mass of the gas, total gas content of the galaxy divided by the mass of the gas plus the mass of the stars total. And you can see that for both either prograde or retrograde orbits, the coalescence fraction is actually highest when the gas fraction is high. And this is telling us that since we know that dynamical friction is the defining mechanism that determines basically the fate of most of the pairs, the massive black hole pairs in the model, this is telling us that it's the gas dynamical friction that matters, right? Because the gas fraction determines the coalescence fraction. Looking at the second panel, it's again coalescence fraction, but in this case versus the primary black hole mass. And you can see that actually the coalescence fraction peaks at about 60 to 80% at lower masses for the primary black hole. And the reason why is that in the TNG50 simulations, lower mass galaxies that host lower mass black holes tend to be more gas rich. So we're basically looking at, again, the other side of the same coin here, which tells us that gaseous dynamical friction plays an important role in the evolution of these pairs and drives them efficiently together. Looking at the third panel, this shows the coalescence fraction versus the mass ratio of the black hole pair, massive black hole pair. And not surprisingly, you see that for either prograde or retrograde orbits, the coalescences happen at the highest rate for comparable mass binaries. The reason is that dynamical friction, again, operates more efficiently on more massive perturbers. So if both black holes are of a comparable mass, dynamical friction will be more efficient on the secondary than if the masses were disparate and the secondary was very low mass compared to the primary. And again, in all cases, we see that prograde massive black hole pairs and prograde orbits lead to more coalescences. Okay, so that is all fine and well. Let's actually now look at the merger rates, the distribution of merger rates as a function of the properties of the merging systems. And let's also see the implications for, say, LISA detection rates, LISA, the Future Space-Based Gravitational Wave Observatory. So let's start with the leftmost panel. I'm just showing this differential merger rates for prograde and low eccentricity systems. For all other configurations, high eccentricity, retrograde, and so on, we basically find similar distributions, but different normalizations. So they're qualitatively similar. So let's just look at this case on the left. This is basically a differential merger rate in terms of the number of coalescences per unit logarithmic bin of binary mass, unit redshift, unit time, but integrated over a period of 4 years, which we pick as a nominal lifetime of the LISA mission. Okay, so differential number over 4 years. And the color here shows that differential coalescence rate. And you can see that basically a hot pixel appears somewhere around a redshift of 1.6. Well, maybe redshift 1 to 2, roughly, just by eyeballing it. And coalescence rate, cosmological coalescence rate, also peaks at lower black hole pair masses. So we're between 10 to the 6 and 10 to the 7 solar masses. And that, again, is the consequence of these galaxies being gas rich and gaseous dynamical friction helping these systems to coalescence. relatively efficiently. The lines, broken lines that you see, are actually representing the signal to noise ratio of LISA detections for those systems that evolve to coalescence. And you can see, not surprisingly, that the highest signal to noise ratio corresponds to the lower mass systems and lower redshifts. And signal to noise ratio of 8 is basically some nominal threshold that implies a LISA detection. So higher signal to noise ratio events are considered detected by LISA, and those that are lower than 8 are not going to be detected.
Tamara,
So
can I ask a question?
Yes, go ahead.
Yeah, what's the typical redshift at which these black holes are seeded in the simulation?
Well, I'm not sure what is the typical redshift where they are seeded. Basically, I have the distribution when they reach their minimal separations, but they are seeded when galaxies and host halos reach some threshold mass. But I don't know what the typical redshift is. I would have to look that up.
Okay. Yeah, I had the impression that that could probably imprint an effect here.
I imagine that that's the case, yes. And I imagine that many will be seeded out to all the way out to redshift of 10 maybe, but probably not in much higher redshift than that, just because the galactic halos need to grow and massive enough in order to plant a 10 to the 6 solar mass black hole seed, right, in them. Okay. All right, so you can see that here nicely the hotspot for the coalescence rate overlaps with LISA contours. So most of these events will be detected by LISA. That's basically the bottom line. Looking at the other two panels, it's basically the differential merger rate shown in the middle panel in terms of the binary mass and the mass ratio. So again, you see that lower binary masses are preferred and equal mass ratios or comparable mass ratios. And these again sit squarely within LISA signal to noise ratio contours of about 100. So most should be detected. And on the right-hand side, you basically see this, the differential coalescence rate in terms of the mass of the stellar bulge of the merger remnant galaxy versus the gas fraction of the remnant galaxy. And you can see that most of the coalescences happen at higher gas fractions, higher than about 0.5, but yeah, they're kind of distributed widely, relatively widely. But you can see this anti-correlation effectively, that more massive bulges have low gas fraction, and because of that, somewhat lower coalescence rate than low mass bulges. But, okay. So what is that we actually calculate for the actual cosmological merger rates? What we find is a rate of about a half of coalescence per year. And then when we calculate LISA detection rates, we find that it's similar but slightly lower value, which kind of makes sense because I just told you based on this that most coalescences should be detected by LISA in this setup. So it's about 0.3, 0.4. These rates, both the cosmological merger rate and the LISA predictions for the LISA detection rate, are actually comparable to those rates that are already in the literature and published, but were drawn from different cosmological simulations. I showed those couple examples here. They include the Eagle simulation, the Illustris simulation, a sister simulation from the same suite as TNG50, as well as the Horizon AGN. but I need to include two cautionary remarks. Basically, our model and all these other models that are based on cosmological simulations really place a lower limit on the LISA detection rate. The reason being that the bulk of the LISA detections will be of coalescences of massive black hole binaries with mass less than 10 to the 6 solar masses. And for us, that's basically the minimum mass of a binary that we model in our model, because we inherit the black hole population from the TNG50. So we are placing a lower limit, and therefore, if the numbers seem low, don't automatically be alarmed. The second cautionary remark is that I just told you moments ago that gas dynamical friction seems to play a very important role in basically driving massive black hole pairs to merger. But in this calculation, in this semi-analytic model, in the results that I showed you thus far, we did not take into account the effect of radiative feedback from an accreting massive black hole, or both of them, on the gas. So we didn't really include that effect in our calculation of gaseous dynamical friction. And we're going to talk about that effect in a moment. So let's try to connect the dots and see if we can predict the properties of dual AGNs that will eventually coalesce. Some will become LISA sources, and what would that connection look like? So in order to do that, we defined theoretical electromagnetic detectability. So what is in that detectability factor? Well, for one, we take into account the instantaneous separation, R of T, of the two massive black holes, because if, say, you wish to detect a dual AGN by taking an image, you will have an easier time detecting a dual AGN with larger separation, given the angular resolution of your instrument. We also include the luminosity ratio of the two AGN as a function of time, because again, if dual AGNs, if the two AGNs have comparable luminosities, it's going to be easier to tell them apart than if one is underluminous, severely underluminous relative to the other. And of course, what matters is a redshift or luminosity distance to the source. So we also include that in this integral. So I'm plotting and showing this detectability factor as a color in the panel on panels at the bottom. So let's first look at the left one that shows detectability as a function of binary mass versus the coalescence redshift for the two massive black holes. You can see that most of those detectable dual AGNs should cluster at low redshifts and again, low binary masses, just because these systems tend to live in gas-rich galaxies. They nicely overlap with LISA signal-to-noise contours. So you could expect that most dual AGNs that you see at a given redshift should be detected by LISA. Looking at the right panel, it's basically a similar statement plotted in terms of binary mass and mass ratio. Again, you see that most of the detectable systems group at comparable mass ratios. Not surprising, because for those you expect to have two AGNs of comparable luminosities, so that would maximize electromagnetic detectability. So there is a nice overlap there. Okay, so that gives you a handle if you wish to calculate basically a coalescence fraction, or a fraction of dual AGN that will eventually lead to a merger. Okay, so far so good. Any questions before?
I guess I have a quick question that follows up with the previous one.
Uh-huh.
I think one of the issues that I wonder about is that you're seeing a lot of the merger times being very short. They're about 100 million years or so at the low end of that plot, if I interpreted that correctly. So it probably happens relatively fast after you're seated in the in the simulation. So is that, I mean, does that worry you at all?
Okay, yes. So what we see is actually that times are relatively long. Let me go back just for a sec to that. So here are the time scales. So the total time on the right-hand side from kiloparsec scales down to coalescence are actually, for majority of our sample, relatively long, on the order of 10 to the 9, 10 to the 8, 10 to the 9 years. So though, as a consequence, really what we see is that by the time they merge, the coalescences really happen at low redshift, just because of a relatively long
Well, the
evolution.
simulation seeding is at super high redshift. It's at, redshift whatever where the halo is forming, and then they're taking the snapshot where they're as close as that it can be resolved in Illustris.
Right, and I'm just sort of wondering because we end up finding that the 10 to the 6 solar mass ones that are most detectable, and that they tend to be at comparable mass ratios. And since these are being seeded as the star formation rate increases in the universe, the bulk of them are probably being seeded right around redshift of 2, then within a gigayear, they're all merged by redshift of 1. And so what we see at redshift of 0 in terms of the detectability might be a small fraction of these things that really have the longest coalescence times and the longest, and the slowest processes associated with them. So that's what I'm trying to reconcile. How much of the other part of the curve where the bulk of the merging is happening is all determined by the assumptions in the simulation and not really by reality in some sense.
Well, it does. I mean, what matters is the total evolution time. Yes, you're right about that. So it's basically from the instant in time where the pair exists at like 1 or 2 kiloparsec separation times the delay time, if you wish, or the merger, that determines the redshift where they coalesce. You can see that a lot of them coalesce. That's basically redshift, low redshift, right? What is this? It corresponds to redshift less than 1, 2, 3, 4, 5, 0.4.
Right. So I mean, maybe if we grow them at a different rate, we could pile up even more merging at low redshift. I was wondering whether that would be another way of making the lower limit that you're deriving even a stronger lower limit. Since a lot depends on how you grow the black hole.
Sorry, gosh, I cannot. I didn't hear the entire sentence, so I'm not sure I understood the question. Do you want to keep this for the end, just because my sound seems to be like just a little bit interrupted? Is it okay to keep this for the end?
We'll talk more at the end. Yeah.
Okay. Okay, so I told you a moment ago that the results that I showed you neglect the effect of radiative feedback from accreting massive black holes. So, okay, what happens if you actually take into account that effect? What are the anticipated effects? And I'm going to illustrate that by showing you these 2 animations, and hopefully they will play on your end, from 2-dimensional radiation hydrodynamic simulation of a million solar mass black hole moving through some idealized uniform neutral background medium from our work a couple of years back. So the left panel shows number density. That's the color scheme. The right-hand side panel shows the temperature of the gas surrounding the black hole. The black hole is centered at 0, 0 coordinate and is moving with a Mach number of 2.7 relative to the background medium. The size of the box is about 1.6 kiloparsecs. So the very moment when the black hole starts accreting and the radiation is emitted from the basically innermost region surrounding the black hole, what we see is that this low density ionized region bubble basically forms around the black hole. It's a tear-shaped region, and it's about a size of 1 kiloparsec in the case of this, this particular setup. Now, why is that interesting? Well, this means that accretion onto that massive black hole will be suppressed because it's now surrounded by a hot, low-density gas. And B, a gravitational gas wake that is exerting dynamical friction onto the black hole may be affected as well, right? Because radiation is basically sweeping away the gas around the black hole. If you actually calculate what is the region around the black hole, massive black hole of this mass, that contributes most of the dynamical friction force, you would find that it's basically an overdense wake that is enclosed within few parsecs from the black hole, right? Few parsecs in the absence of radiative feedback. So you can see that this bubble being much larger than that implies that this overdense gas wake will be swept away by radiation, certainly perturbed, if not obliterated. Okay, well, with that in mind, I will tell you that by actually calculating explicitly the gas's dynamical friction force in this setup, we find that this radiative feedback renders it completely ineffective. And what I'm showing in these 3 panels here are basically snapshots from 3 different simulations. One where the black hole is moving with a Mach number of 1/2, one where it's moving with a Mach number 1 and Mach number of 2. And again, number density, gas number density is what's shown. And what I wanted to show you is not only that gas's dynamical friction is rendered ineffective in these scenarios, but in the second and third panel, what you can see is that ahead, upstream from the black hole, there is an overdense bow shock that is forming ahead of the black hole. And this overdensity in gas interacts with the black hole and it actually accelerates it. But there is no dense wake behind the black hole to kind of counteract that. So contrary to the prediction of the classical gaseous dynamical friction, where you expect the wake behind the black hole to decelerate the black hole or sap its orbital energy, what we find is that in the presence of radiative feedback, the black hole actually is accelerated. So that, of course, does not happen in every case, and it doesn't happen forever. So black hole is not going to be accelerated to the speed of light. There is a set of criteria that determine when gas dynamical friction is actually behaving as negative dynamical friction. And you can see that set of criteria shown at the bottom. This happens when the Mach number of the black hole is less than 4. This follows straight from the jump conditions, because for Mach numbers higher than 4, this bow shock, overdense bow shock, just is destabilized and it falls apart. So you're back to effectively Bondi-Hoyle-Littleton accretion and classical dynamical friction picture. The second criterion basically follows from the requirement that the radius of the ionized region, or the Stromgren sphere, if you wish, is larger than the Bondi radius, or the radius of gravitational dominance of the black hole. In that case, basically, the radiation leads to the formation of this large bubble. And you can see in that criterion, as it is written, that it's basically a product of the black hole mass and the number density of the gas at infinity, where it's not perturbed basically by the gravity of the black hole. That these two should basically be less than 10 to the 9 solar masses per centimeter cube. So what this means is that negative dynamical friction will more strongly affect lower mass black holes, right? Those of 10 to the 6 solar masses rather than 10 to the 9, because they will fall within this criterion. They will satisfy this inequality more easily. So those massive black holes will have fewer means of reaching the center of a remnant galaxy and merging with a counterpart black hole. And these, of course, are exactly the massive black holes that are of interest to LISA, Gravitational Wave Observatory. Okay. Moving on. So how does this affect the merger rates that we calculate? So if we fold this effect of radiative feedback, where we find that there is negative dynamical friction force that accelerates the black hole, and we recalculate the cosmological merger rates for massive black holes in this sample that we consider, and LISA detection rates, this is what we find. So starting with the left panel, again, this is the differential coalescence rate shown in terms of the binary mass and redshift of coalescence. You can now see that most of the coalescences happen at higher binary masses. So it used to be that lower mass binaries were greatly helped by gas dynamical friction before, when we did not consider the radiative feedback. Now, when we take it into account, the mergers of those low mass binaries are affected by negative dynamical friction. And what we see is that merger rates peak at higher masses of about 10 to the 8 solar masses. And these now, the hot pixels now don't line up necessarily with LISA signal to noise ratio contours. So it means that LISA would not necessarily see most of those mergers because those black holes are too massive. Similar is the case for the second panel, where you see the differential merger rate in terms of the binary mass and the mass ratio. LISA will pick up some because the signal to noise ratio of 8 kind of encloses some fraction of mergers, but most will actually be out of reach for LISA. And on the right, the last panel shows differential coalescence rate in terms of the stellar bulge mass and the gas fraction of the remnant galaxy. You can now see that the peak of the cosmological merger rate is located basically at values of higher stellar bulge mass and very low gas fractions, because these galaxies are not affected by negative dynamical friction. If there's no gas, there's no negative gases dynamical friction. So these systems merge entirely due to the effect of basically stellar processes acting on the two black holes. And these massive systems actually will be out of reach for LISA, right? Because it mostly will be detecting lower mass binaries. So just to summarize what is that we calculate, when we take into account the effect of radiative feedback, as we know it from simulations thus far, we find a cosmological merger rate of about 0.1 per year and a LISA detection rate, which is much lower. It's now 0.02 per year. And this at first may be alarming, because if LISA flies for even 4, maybe even 10 years, that indicates less than one event detected by LISA. But again, I will just remind you that this is a lower limit. So we're not making a prediction that LISA will not see anything. We are not. But what we are seeing is that radiative feedback, if it operates in a way that we see in simulations, we and some other groups, then it may make a difference. It may make a dent in LISA detection rates. Just to remind you, what are the numbers that we calculated in the absence of radiative feedback? I showed the line at the bottom. So those are the rates that we calculated. And I showed you before, okay? Okay, so radiative feedback matters. It may make a big impact. So this is my final slide. Let me show you, basically now we learned something about the properties of dual AGNs that will eventually lead to coalescence of massive black holes, and some of them maybe even become LISA sources. Let's see what is the fraction of those that coalesce, so that if we measure some number of dual AGNs on the sky, we can basically, in statistical sense, predict what the coalescence, cosmological coalescence rate of massive black holes is. So on the left, coalescence fractions are shown versus the redshift at which dual AGNs are observed at kiloparsec separations. And this first left panel is for the calculation without any effect of radiative feedback. We basically made a cut in terms of the bolometric luminosity, which is the only one that we can measure or model rather, proportional to the accretion that rate onto the massive black holes. And we find that. Let's first look at the blue curve here. The blue curve represents dual AGNs at separation of about 400 parsecs. So if we look at the redshift of 2, say, we find that any dual AGNs at redshift of 2 that have separation of 400 parsecs should pretty much merge by the redshift of 0. And the same is true for, obviously, dual AGNs with smaller separations, like 100 parsecs. But moving on to larger separations, it takes a longer time for, say, duals at separation of 700 parsecs to merge. So we see that it's only a fraction of about 70 to 80% of them that merge by the redshift of 0. And at the bottom, the red curve shows basically this fraction for all possible pairs in the simulation. In the presence of radiative feedback, the picture changes a little bit. Again, coalescence fraction versus the redshift of a precursor dual AGN shows that now at redshift of 2, we don't see any dual AGNs that at redshift of 2 that have separation of 100 parsecs, because in the presence of radiative feedback, all massive black hole pairs evolve very slowly. They really don't reach such small separations. So we don't have any in our sample. When it comes to the blue squares, separation of 400 parsecs, we have some of those, but they also, only a small fraction at redshift of 2 will evolve to coalescence down to redshift of 0, even if their separation is only 400 parsecs. And you can see basically the rate or the coalescence fraction being even lower for those dual AGN at redshift 2 that have a separation of 700 parsecs. Only about 20% of those will evolve to coalescence. And the red curve shows the total for all possible separations. So if indeed the nature operates in this way, then we can use predictions like this from theoretical models to convert the number of observed dual AGNs in the sky to some expectations for cosmological coalescence rates and perhaps even LISA detection rates. So we're almost out of time. I'll put up my summary. Dual AGNs remain the most explicit observational evidence for massive black hole pairs that we have at this point in time. And it would be great if we can actually use them to make predictions for the rate of mergers of massive black holes in the universe. With calculations that connect the nature and properties of dual AGNs and to coalescences, we can cautiously use them to infer the coalescence rates, being aware of caveats and our inadvertently limited knowledge, right, in theoretical models. We find that for a population of massive black hole pairs that actually coalesce within the Hubble time, or more importantly by redshift 0, dynamical friction is the most important mechanism that determines their merger rate. So that's interesting. That is interesting, and it means that when coalescence rate is measured by gravitational wave observatories for a population of massive black holes, that that rate will directly constrain the efficiency of dynamical friction. So for the first time, perhaps we'll be able to test this theoretical concept because that's what dynamical friction is at this point. It's a basically theoretical construct that is yet to be tested through observations. Without radiative feedback, our model predicts a merger rate that is about half and LISA detection rate that is slightly lower than that. This is comparable to works in the literature. Most of the mergers in our calculation originate from the mass range of 10 to the 6 to 10 to the 7, but again, my cautionary remark is that is because we don't capture the evolution of black holes that have mass lower than 10 to the 6. And the peak of the coalescences happens at redshift of around 2. And for LISA, we calculate that most of those detections should happen at signal to noise ratio about 100, which is pretty loud for LISA. With radiative feedback, we find a striking reduction of the binary coalescence rate, cosmological coalescence rate, by a factor of 78%. And even more dramatic reduction of a LISA detection rate by 98%, as well as a reduction in the signal to noise ratio. So I don't want to be alarmist, but my conclusion is that that it's important to understand the effect of radiative feedback on the LISA coalescence rate or detection rate, because it may be important, may make a dent. So I'll stop there. Thank you very much for
Thank you, Tamara.
For your attention, and I'm happy to take any questions.
So we're at the hour, but Tamara, if you have 5 more minutes to stay, I see there's at least some questions online. Dan, you can go ahead and unmute, if you have to leave at this point in the process.
Yeah, thanks for teaching me a lot about coalescing black holes. Without waiting for LISA, if we measured like a distribution of pair separations, might you or have you predicted what that distribution might be? And it seems like separations less than a kiloparsec are especially important to see how pairs have coalesced from their initial formation down toward merging and where they might stall.
Right. So yes, in principle, we can make predictions for distribution of separations in this model. Our model basically looks at separations lower than 1 or 2 kiloparsecs, mostly because by then we expect the 2 stellar bulges to merge into 1. So this is when we expect the dynamical friction should start being important rather than larger scale tidal interactions of the 2 galaxies. So in order to basically test this picture, we would need a reasonably large statistically representative sample of dual AGNs with separations that are lower than a few kiloparsecs. So yeah, hopefully there are already some detections, a number of dual AGNs are available, but not yet a full statistical sample that we could use to dissect them like this and basically make predictions about coalescence rates and so on.
Hi, I have a question about your radiative feedback. Do you have a sense at what Eddington ratio you would need for this to have a significant effect? My intuition is that an offset black hole would probably have a lower Eddington rate and would probably turn into a radiatively inefficient disk anyway, so maybe this isn't too catastrophic.
So I'm trying to remember. So your question is, what is the Eddington luminosity at which this affect negative dynamical friction?
Right.
Is it-
Yeah, does it need to be, at AGN levels? And potentially, does that mean, could we even rule this out observationally if they might be
Right.
bright?
So there is no single specific value that I can give you, but I can tell you that what simulations of accreting massive black holes or any black holes, intermediate mass, are finding is that when radiative feedback is effective at suppressing accretion, when it's effective at creating this kind of ionized bubble, the accretion rate onto the black hole is reduced by a factor of about 100 relative to the scenario when there is no radiative feedback. So basically a scenario where when there is no radiative feedback is, whatever luminosity, whatever baseline luminosity you start with, in the presence of radiative feedback, it will be about a factor of 100 lower m dot. So it will be indeed even lower. If you started at Eddington, it would be 100 of Eddington at that point. So yeah, you're right. It may be that for some systems, their luminosity would be reduced sufficiently so that there would be a radiated inefficient accretion regime.
Interesting. Well, we should probably stop there. Tamara, thank you so much for a really thought-provoking talk. I think it's going to be amazing to see how the mass distributions that we uncover, whether something I took was, they encode the underlying mass distribution, but they also encode all this physics of what actually merges as opposed to just what sort of stays separate. It's gonna be really amazing to see.
Well, thank you very much for your attention and for your questions. And feel free to email me if you think of any other questions in the meantime.
Amazing. Thank you so much.
Thanks a lot.